and welcome to the Spatial Structures Movers and Shakers interview series, hosted by the University of Surrey's Spatial Structures Research Centre. My name is Mark Richardson, and I'm delighted to be joined by Su-Duo Xue, who is a professor at Beijing University of Technology and the president of China's Association for Spatial Structures. Professor Xue is a member of the IASS Executive Council and co-chair of Working Group 8 on Metal Spatial Structures. He is a member of the Editorial Committee of the Journal of the ISS and a member of the Editorial Board of the International Journal of Space Structures. Su-Duo's research interests include shell and spatial structures, earthquake engineering, and structural vibration control. Professor Xue, thanks very much for taking the time to join us today.
Okay, it's my pleasure to be here. Thank you.
It's an absolute pleasure to have you joining us on the Movers and Shakers interview series. Thank you for taking the time to join us. Would you be able to start by giving us an idea or some information about the spatial structures community in your region in China?
Okay, regarding spatial structure community in China, I think two communities should be mentioned. One is Spatial Structures Committee. Another one is China Association for Spatial Structures. The Spatial Structure Committee in China was founded in 1982. It is an academic organization aiming at academic exchanges. By organizing national conferences on spatial structures every 2 years, the academic research and technology level of spatial structures in China have been greatly promoted over the past years. This year is the 14th anniversary of the committee, and next month we will hold the 14th anniversary conference on spatial structures. China Association for Spatial Structures was founded in 1993. Now I am the president of the association. It is an industry association constituted mainly by enterprises engaged in spatial structure design, manufacture, and construction. Of course, research institutes and universities are also included. The establishment of the association plays an important role for development and engineering practice of spatial structures in China. And next year will be the 30th anniversary of the association, and we will have the anniversary conferences to celebrate this event. Okay.
Thank you, Professor. Very, very helpful insight there. Would you also be able to provide us with an overview of your career journey to date?
Yeah. My career journey for spatial structures started in 1983 when I was a postgraduate student at Beijing University of Technology. During my postgraduate studies, I learned many knowledges about spatial structures. My postgraduate research was related to the study of the structural system of Anhui gymnasium, which was a transversely stiffened cable system, and was the first spatial structure I involved during my career. I will talk about this later in my middle section. At the time of my graduate study, an important event for me was the participation of the second national conference on spatial structure in 1984. At that time, I was thinking about what I should do for my postgraduate research. By attending this conference, I had a good understanding for the state-of-the-art researches and engineering practices of spatial structures and obtained valuable knowledge and useful information. I also talked to many leading experts for their advice for my research topics. This helped me a lot for my postgraduate research and even influenced me many for later career in spatial structures. In 1986, I obtained my master's degree and became a teacher at the Beijing University of Technology. I worked mainly on spatial structures research at the university. Afterwards, I went to Hong Kong Polytechnic University in 1995 for my further PhD studies. At that time, the Qingma Bridge was being constructed. It is a long cable suspension bridge with a length of 2160 meters and a main span of 1377 meters. It is the world's longest suspension bridge for both road and railway. I took part in many of the work for the analysis and field measurement of the bridge to learn about its behaviors and every construction stage, from which I obtained more professional knowledge. The topic of my PhD research was about wind-induced vibration control of suspension bridges. From the research, I further expanded my knowledge of wind engineering and vibration control. The experience of my PhD study laid a good foundation for my later career. Upon graduation from Hong Kong Polytechnic University in 1998, I returned back to Beijing University of Technology for continued research in the field of spatial structure. Now, it has passed 24 years since I came back from Hong Kong.
Thank you very much, Professor. And final question in our introductory section. Could you tell us about a research paper or project you are currently working on at the moment?
Okay. Actually, I'm working on a book currently. It is about seismic design theory and seismic mitigation technique for spatial structures. You know, I worked on seismic design and seismic mitigation of spatial structures for many years. In this book, many key issues for seismic design and seismic mitigation of spatial structures will be involved, which include the multidimensional seismic analysis method, soil structure interaction, integrated design method, considering both roof and supporting structure, seismic performance and progressive collapse analysis and strong earthquake, seismic isolation and vibration control for spatial structures, and large-scale shaking table test study is central. In addition, examples in engineering applications are also included. This book is expected to be finished at the end of this year and will be published next year.
Professor, thank you very much for telling us about that. And we very much look forward to your book when it is available for the spatial structures community to enjoy. So thank you for letting us know. Well, let's move on to the middle section of our interview, which is entitled Your Space, Your Structure. So I will hand over the presentation to Professor Xue, and he will be presenting for 10 to 15 minutes on a topic of personal interest to him. So without further ado, over to you, Professor.
So in this part, I will talk about two topics. First, I will introduce the first spatial structure I involved during my career. And then I will introduce the loop-free cable supported structure that I proposed. The first spatial structure I involved is the Anhui Gymnasium. When I was a postgraduate student from 1983 to 1986, I involved this gymnasium, which is under for the stage of the pre-study of the structure system. So I involved for the investigation for structural behaviors of the proposed structure system. And this is hexagonal in shape with a size of 17.2 meters in long axis and 6.9 meters in the shorter axis. This structure is proposed by Professor Tianti Lan. It is a single curvature transversely different cable system. The single curvature cable suspension roof is in the early applications. It is usually use the heavy cladding or heavy loads for the establishment for the pre-stresses of cables. But that is not a good method because we have to use additional loads for the roof and result in the waste of the material. So how can we employ the pre-stresses for the cables is a main concern for this kind of structure. So Professor Lan proposed using the stiffening element to arrange coils overly around for the cables. Then we may use trusses or cables or beams on the cables. By pressing down the ends of the supporting ends of the trusses or beams, the pre-stresses for the cables can be resulted in, and which will have a good stiffness for the structure. So for this new proposed structure system, we have many new key issues to be studied, like the optimal structural arrangement, the establishment of pre-tensions for cables, and the structural behaviors and the loading, and the force distribution and displacement, and the dynamic behaviors of the system, and also for the nonlinear performance. So I took part in most of the analysis and investigation for this kind of system. And finally, I finished my master's degree thesis by a study on the dynamic characteristics of cable truss beam system. When I graduated from the university in 1987, we have international colloquium on space structures for sport buildings in Beijing. And then on this conference, I published my first English paper for the dynamic characteristics and the response of cable structures and the general program on microcomputer. This is my first publication written by English. And also, it is my first time to present paper and then international conference. And this conference, I learned a lot about the current research status of the international spatial structures. So I learned more knowledge about spatial structures. And I also met and talked to many leading professors and experts like the Su-Duo Xue and also Markowski and Newton from Surrey. And by attending this conference, it has influenced me very a lot for my later career. Since then, I have been doing research in the field of spatial structures. The topic I have studied includes the innovation for spatial structural systems and structural behaviors of spatial structure and static and dynamic loading, nonlinear analysis method, seismic performance and seismic design, multidimensional seismic analysis method for spatial structures, and random vibration analysis, wind-induced vibration analysis, and cell structure interaction, seismic isolation and vibration control for spatial structures, and also engineering applications of spatial structures. And I also involved most of the type of spatial structures, like the spatial grid structures, cable structures, memory structures, and also hyperstructure systems. Second, I will introduce the loop-free cable supported system, which I proposed. For cable structures, the pre-stressed cable structure is very commonly used for the stadium and the gymnasium. For this kind of structure, we usually use ring cables, like for the wheel spoke cable truss, like this one. Then we have the inner ring cables here. Then cable truss arranged between the outer ring beam and the inner ring cable. And all the cable trusses are arranged between the inner ring cables and outer ring beams. And also for the single layer wheel spoke cable net, we also have the inner ring cables and the radial cables, and outside the outer ring beams. And also for the suspend dome, we also use the ring cables. But for this type of structure, we have two key problems. One is the inner ring cables have very large forces here. And another one is if the inner ring cable loses its stress and failure, the structure may have a danger for continuous collapse. So like this, if the ring cable cut off and loses its failure and breaks, the whole structure may have the continuous collapse for this structure. So this kind of structure, also it has many applications in the real structure, but it has potential problems for the safety. The question is whether we have some measures to solve this problem. So for this problem, I propose we can use loop-free structure. I propose 3 types for the loop-free cable supported structure. For the first type is the loop-free cable truss, like this one. So here I use the cable trusses reached crossoverly around the roof. And without inner ring cables here. So you can see for this arrangement, the structure roof can also have the large opening in the center. Then we will satisfy the requirements for the stadium with a large opening. And the crossover arranged cable trusses are fixed directly on the end of the outer ring beam. So you can see if the cables or nodes or the sports failure, only local failure may occur. But if this area breaks, this area of the structure is still safe. So it has a very good capacity for the resisting progressive collapse of the structure. So it have a good ability for resisting the continuous collapse. So this we have a video show for the arrangement. You can see the crossover arrangement for the structure, and it is faced on both ends of the outer ring beam. Another one is loop-free single-layer cable supported structure. So for this one, the inner ring cable are not used for this structure, and the crossover cables here. So by this arrangement, the roofs of the structure can also be used for the large stadium and for the covering. This is a good solve for this one, for this kind of structure. The third structure I propose is the loop-free suspend dome. The suspend dome is originally developed by Professor Mario Kawakuchi, and it has many applications in the real projects. But here we also use the crossed cables reached crossoverly, and no ring cables are used. So by this way, we can also establish the structure system by the single layer lantern dome in the upper roof, and we use the loop-free cable supporting system lower for the supporting system. Yeah, you can see the cables are crossoverly arranged, and no ring cables here. The first type I proposed is a loop-free cable-supported grid structure with large opening. For the stadium, sometimes we use grid structure for the upper layer, the covering. So we can also use the cables arranged crossoverly for the supporting structure, for like this one. So by this way, we can also solve the problem for the ring cables between, which may induce the collapse of the structure. So for the proposed structure, we carried out many theoretical and experimental investigations, which include the geometric modeling, form fitting, joint design, construction method, static and dynamic behaviors, and performance for resisting progressive collapse, and the roof covering effect. Let's take a loop-free cable structure as an example. For the geometrical formulation and method modeling of the structure, we can establish the geometrical formula by the system X, Y, and Z coordinates. Then we will have the cylindrical coordinate system like this, and also we have the coordinates phi and r and omega, and also for the coordinates c and play in the play third here. So we can have some controlled functions for this. By research, we can find the geometry is controlled by 3 independent variables and 2 functions. The 3 independent variables are the Pn is here, the number of cable trusses, and Pc is the number of circles along a cable truss, like this one. So for one cable truss structure, the number of the circles, and R1 is the radius of the structure, like this one. So we have 2 functions, fx and gx. And we also introduce another ceiling here. Ceiling is the ratio of the rise of the sunk and the rise of the plate, the cable truss. By this, we can guarantee at least one self-stress state. So by the formulation and the method modeling, we can write our computer program and can easily get the structure configuration if we give the parameters for PC, Pn, R1, C0, and also for the functions. Then we can get the structure configuration very, very easily. Also, we carried out the experimental investigation for the static behaviors and loading, the erection method, and also for the performance for resisting progressive collapse. For the static behaviors and the loading, we use 3 cases for the loading. Case 1 is the symmetric load, uniformly distributed load. and case 2 are asymmetrical load, 1/2 layout for the loss. And the case 3 is also asymmetrical load, is 1/4 layout for the loss. So by the study, we found the structure have a very good structural stiffness and a very good performance for irregularly distributed load. We propose 3 freeze contraction methods for this kind of structure. First freeze is assembly all members on the ground. So first, we assembly all members on ground. And second is the lifting operation. We can divide the lifting operation by several stages. Here, for the experiments, we use 4 stages. From the initial and to the first stage, and to the second stage, and to the third stage, and to the fourth. And the third freeze is also the final stage. We regulate the geometry and forces. Then we can make this structure have very good stiffness by regulating the geometry and forces. And we also use the simulation for the lifting operation. We propose 3 methods for the lifting operation, and the inverse forward simulation method. For the inverse stage is a various tangent state to the initial hanging state. Also, for the forward stage is from the initial hanging state to the final state of lifting operation. By this, we can get all the intermediate state of the structure and every stage. So you can see this is a simulation process. Yeah. So from the beginning, then to the initial, then finally reach to the beginning. This is the final. This is the initial and to the final. And also for the final state and the various tangent state, we just use regulate the final to the final stage. And also we, for the experiment verification, we found the experimental values agrees well with the numerical results. You can see it's well agreed. For the test for resisting progressive collapse, we use 3 schemes. One is cutting of 1 cable segment, and for this is cutting 2 segments of cable, and this is cutting of 3 segments of cable. So using the 3 cable counter plans, we found this is one of the stage when a cable segment is cut off. From this study, we found the cable rupture induces only local damage. This structure has a good capacity for resisting progressive collapse. After our research, we proposed our structure to a real engineering projects. It is a gym of Ojai Olympic Sports Center. This structure is have a cylindrical surface and is a circular plane. We propose using loop-free suspend dome, and the roof span is 100.6 meters. So this is a normal suspend dome with ring cable, and this is a loop-free suspend dome we proposed. You can see for the normal ring dome, if the ring cable loses its stress and breaks, continuous collapse of the structure may occur. For the loop-free cable suspend dome, cables are arranged crossover and work independently. Even if one cable segment or node fails, the whole structure will have a good capacity of resisting progressive collapse. This is the final structure configuration for the Ojai gymnasium. So we use the lattice dome in the upper roof, and also for the coast cable system here, and we have the supporting system here, and finally we have the overall structure. And this is a loop-free cable arrangement, like the red circle, red line. And this is final arrangement for, we have 3 layers. This one layer and the second layer and the third layer. We made a comparison of 2 structure types. One is for the loop-free suspend dome, and this is for the normal suspend dome. We have the comparison for the steel consumption, number for the cables, and for the number of junction ends for pretension, a number of cast steel joints, and also for the structural behavior and safety. From the steel consumption, you can see for the cables, the loop-free cable suspend dome have a better economy. You save about 20% steel consumption for cables. And for the cables, we have only 20% the number of normal suspend dome. And for the number of junction ends, we found a loop-free cable suspend dome only have 48 numbers. So it has a fewer number of junction ends, only 40% the number of normal dome. So for the number of cable cast steel joints, for the loop-free cable suspend dome, we have 120 numbers, and for the normal suspend dome is 240. So it uses fewer kinds of steel joints, only half the number of normal suspend dome. it is said that the cost for cancer steel joints will be greatly reduced. And for the structural behavior and safety, the loop-free cable system dome. No progressive collapse occurs when 5 cables break. But for the normal system dome, progressive collapse occurs when outer ring cable breaks. And for the loop-free cable system dome, we have a good performance for irregularly distributed load. And for the normal system dome, it is sensitive to irregularly distributed load. This shows the force transfer path for the loop-free system dome. You can see the load is transferred to the strut and to the cable and then to the support. But for normal system dome, the roof load transferred to the strut, then ring cable, then radial cable, and finally to the support. So the loop-free system dome have direct force transfer paths, and the forces in the cables are evenly distributed. This shows the vertical displacement for various combinations of load. We can see that all the all the requirements are required for the design specification and the different load combinations. And we also make the analysis under strong earthquake. We can see for roof members, most components reach 0.2 to 0.3 times yield bearing capacity. A few components 50% to 3% reach 0.4 to 0.6 times yield bearing capacity. For cables, the maximum tension forces is less than 0.4 times the breaking load, and none of the cables turns into slack. The analysis for resisting progressive collapse we use for the removal of upper chord and upper chord ring chord, and also for removal of upper chord radial cable. We made 5 cases for the study. It is found that no progressive collapse occurs when the upper chord rod strut and the support are removed separately. And we also make the analysis for resisting progressive collapse induced by cable failure. So we use nonlinear dynamic method for progressive collapse analysis, and we select 5 cables failure respectively. We found that when 5 cables break, only local large deformation near the break cables take place. The maximum displacement for the structure is 430 millimeters. So no progressive collapse occurs. So it is said that it has a very good capacity of resisting progressive collapse. This is the final the pictures under construction. Another example is the schematic design for Linyi Olympic Sports Center Stadium. This stadium has a single layer cable system, and it's a center-shaped roof surface with a roof span for 288 meter and 286 meter. We compare two types of structure schemes. This is a system with ring cable, and this is a system without ring cable. That is we proposed loop-free system. So I also make the comparison of these two structure systems for the system with one is with ring cables, another is without ring cable, and we also make the for the steel consumption, the number of cables, the number of joints, and deflection, and also the cable forces for the two structure systems. We found that by using the system without ring cable, we can save 38% cable steel consumptions and save 18% steel consumption in total. And for the number of cables, we have 43% the number of the waste ring cable. And we have few number of joints, less than half of the with ring cable type in total. So the cost for joints will be reduced and the construction will be more convenient. Also, we have low deflection, and this behaves a greater structural stiffness. And we have small cable forces that making construction more easily. We also make the analysis for resisting progressive collapse. For this is without ring cable is loop free, and this is with ring cable. So it is found that for with ring cable system, the progressive collapse took place when the outer ring cable loop breaks, but for the non-ring cable system, no progressive collapse occurred after 5 cables failure. So finally, we come to the summary for the advantage of loop-free cable supported system. It's a good capacity of resisting progressive collapse, and we have high structural stiffness, and we have good performance for irregularly distributed load, more evenly distributed cable forces, and more direct cable force transmission. We have small cable forces that making construction more easily, and of course, it is have a better economy. So this is all for my presentation. Thank you.
Professor Xue, thanks very much for taking us through your presentation there, which covered a number of elements, including loop-free cable support structures. Very fascinating area of engineering to learn about, and also great to see some familiar faces in your presentation in the form of Professor Mikowski and Professor Nushin, who we are very familiar with on the Spatial Structures Movers and Shakers series. So thank you for the presentation today. We're now going to move on to the end section of the interview, which looks towards the future of spatial structures and particularly questions around sustainability. Professor, I wonder, what are your personal views with respect to the question of sustainability and spatial structure projects? How can sustainability be improved within our community and its outputs?
Okay, sure. Sustainability has been a great concern to our society, especially for the current global climate and environmental problems. Regarding sustainability in spatial structure projects and sustainability improvement within our community, I think there are at least two aspects involved. The first one is spatial structure shows the sustainable development of society. And the second is sustainability in construction process of spatial structure. For the first aspect, spatial structures can be used in environmental protection, such as the covering of chemical plants or sewage treatment plants, the shelter of coal jars or stock yards, etc., from which the emission of harmful gases or dusts can be controlled and treated so that our living environment can be improved. For the second aspect, the sustainability in construction of space structure deals with many factors, such as sustainable site planning, environmental protection and control, resource utilization and compensation, green and recyclable material selection, high efficiency structural system, full life cycle design, low carbon and energy saving measures, green construction, post-match use of competition venues, multifunctional utilization, and many others. Through these combined measures, structural and social sustainability can be achieved. Okay.
Thank you very much, Professor. Well, that's all we've got time for on today's Movers and Structures, Movers and Shakers interview. Thank you very much for taking the time to join us today. To those watching, if you've enjoyed this video or indeed any in the Movers and Shakers interview series, please remember to like, share and comment. All your views and thoughts are very welcome. And do follow Spatial Structures on LinkedIn, Facebook, Instagram, Twitter and Bilibili. Details of our social channels can be found in the description section below. Well, that just leaves me to thank Su-Duo Xue once again for joining us today. It was a real privilege to speak to you and to learn more about your work in the field of spatial structures. Thank you very much for your time, and hopefully we'll get the chance to speak to you again on the Movers and Shakers interview series.
Thank you.
Bye for now.
Bye.